Hello, I'm RJ Alba, and this is my Electromechanical Systems project. So right here is a video of my motor. And right here, these two vertical blocks are my stator with the field magnets on them. They're permanent magnets. In the middle rotating is my rotor. It has 3 coils. And here I am demonstrating that I can disconnect it and let it reconnect, and it will self-start. So it starts on its own. I don't need to flick it or anything. So here's a video of me explaining how this motor works. So let's say this is the positive terminal and this is a negative terminal. So right here, this commutator segment is connected to the positive terminal. So the current is going to go around through this coil in this direction from positive to the negative. So for the right-hand rule, our magnetic field is going to be in the direction of my thumb this way. And let's say our field magnets are oriented in such a way that our magnetic field is pointing this way. So this coil is going to want to align with that magnetic field, point that way. So it's going to be like this, and it's going to want to turn that way. So the clockwise torque is going to be induced. Now for this coil, let's look what's going on. So right here it's connected to the positive terminal. So the current is going to go that way. So the right-hand rule, our magnetic field is going to be the direction of my thumb, and it's also going to want to be in line with our field current, our field magnets, like this. So it's going to be like that to that, like that. So it's also going to have the clockwise torque induced on it. Now, for this commutator segment underneath, it is not connected to either the positive nor the negative terminal, but it is connecting this coil with this coil. So our current is exiting out of this coil into this coil, and in this coil the current is going to be in that direction. So per the right-hand rule, our magnetic field is going to be pointing in the direction of my thumb, and it's still going to want to be pointing this way. So a clockwise torque will also be induced on that coil. So what happens once these 3 electromagnets find a stable position? Well, as you can see right here, our commutator segment right here is connected to the positive terminal, but as I move it, rotate it in clockwise direction, it is no longer connected to the positive terminal because there's a break right here in the commutator's rings. And so as our motor rotates, our connections actually rotate with it, they change, and this is what keeps the motor spinning. So let me remind you that these 2 vertical blocks right here with the magnets on them constitute the stator. So if we were to remove these 2 blocks with the magnets on them, the rotor would no longer have a magnetic field to interact with. And this interaction between the 2 magnetic fields, the rotor and the stator, is what causes mechanical rotation. So without one of the 2, no mechanical rotation can occur. So polarity and direction. So let's say that this brush right here is the positive terminal, and this other brush is the negative terminal. If that's the case, it will spin this direction. And if we were to flip the polarity such that this would now be the positive terminal, and this would be the negative terminal, then the motor would spin the other direction. And that is because as we flip the voltage polarity, we're essentially flipping the direction of current, and the direction of current is what determines magnetic polarity, as I explained earlier in the video, due to the right-hand rule. So my torque, my motor did not visibly display a change in torque, and that's because it had a constant load, which was just the motor itself at no load. Destruction testing. How would I perform destruction testing? I would do so by increasing the voltage until mechanical failure occurs. And mechanical failure will occur because as I increase the voltage, the speed at which it spins will increase until it can no longer sustain such high speeds. So as you saw, my motor was self-starting, and that was, as I explained in my video, due to the way the commutator segments and the windings are connected. My motor was not self-stopping, but you could implement that functionality by connecting the terminals to a relay and connecting that relay to a microcontroller, which is programmed to trip that relay whenever a certain event occurs, and you could detect that event, whatever event you want, with some sensor and implement it in that circuit. So how would I load up my motor? So I actually have a little piece of tape on my motor right here, and that's technically its load right now. And so for any load, you would just do the same thing as I did with this tape, just secure it to its shaft. And for a substantial load, you would notice its rotation slow down because as the torque it delivers is required to increase because of the higher load. So torque increases and its frequency or its speed of rotation will decrease. And that's assuming that it has a constant power, it's given a constant power. So in order to compensate for that increase in torque, the frequency will decrease. Speed control. How would I control the speed of my motor? So as I said before, voltage is related to the frequency at which the motor spins. So if I wanted to increase the speed, I would increase the voltage or boost the voltage. And if I wanted to decrease the speed, I would buck the voltage. And I would do this with a buck boost converter. And that would just be done by varying the duty cycle appropriately on the buck boost converter. And the reason I would use a buck boost converter is because this is a DC machine. So frequency measurement, how would I measure how fast my motor spins? So one way I could do that is by using a sensor that detects when a cycle occurs. So perhaps I have a little laser, and whenever that laser is broken by this little piece of tape, that happens once per cycle, and I could calculate how many times that happens per minute, and that would be my rotations per minute. AC power. If I powered my motor with AC power, it would not work. One problem is that a slipping poles situation could occur so that the current is alternating so quick at 60 hertz, though that's quick enough such that my motor would not be able to react quickly enough, and it would just shake as the current is alternating directions. Its magnetic field will also alternate with it, so it would just shake with it pretty much, as it doesn't have a momentum to keep up with that the frequency of the electrical supply given. And even if measures were taken to avoid that slipping poles situation, such as giving it a little kick such that it would have momentum to keep up with the electrical frequency, the commutator rings would further alternate that alternating current, so the motor would just behave erratically. It wouldn't do you any good. Okay.
So DC generator, I could actually make this motor into a DC generator just by simply spinning it, and a voltage would appear at the terminals. And I would expect to produce as much voltage proportional to how fast I can spin it. Again, as I said, voltage is directly related to the frequency, mechanical frequency of this machine. So right here, I actually have my first design of my motor, and it didn't work, and I suspect it's because the rotor was too tightly fitted into the stator right here, so there was a lot of friction between the rotor and stator, and there wasn't enough torque to overcome that friction. And I also suspect that even without the stator being too tightly fit, the rotor itself was too heavy as because of these metal laminations. And so that's why I went on to my second design that you saw, and that at first did not actually work. And that was because it was not giving enough current. I had two DC power supplies, and I put them in series at first to give them a high voltage. It was 30 volts, and so I started off with that 30 volts. It still didn't spin, so I suspected it needed more current, not more voltage, because the current is what gives that torque. So so I instead of putting the two DC power supplies in series, I put them in parallel, and that gave it enough current and therefore enough torque, and that's what made it spin. Okay. So right here is actually a video of me spinning the rotor of my motor and making it behave like a generator. So right here you will see the voltage at the output of my terminals. And right now it's giving a positive voltage as I spin this way. Now I'm going to spin the other way, and you can notice a negative voltage on the multimeter. Thank you. That is my project.